Good morning all. Today we are going to discuss about the concept of functions. So first we will discuss about some basic terminology. What is a function? So if a and b are any two non-empty sets, a function f from a to b is said to be assignment of exactly one element of b to every element of a. So if f is a function defined from a to b, we will represent as f of a equal b. That means every element of A should be mapped to exactly one element of B. Then we can say that it is a function. So functions are also called as mappings or transformations. So this is a graphical representation of functions. So using Venn diagram, we can represent a function like this. Here f is a function from A to B. So every element of A will be mapped to unique element of B. So this is the Venn diagram representation of a function. So this is graph, this is plot. So in all these ways we can represent a function. Here some examples for mappings which are not functions. See here this is not a function because here from A there is no mapping to element of B. That's why this is not a function. So if a mapping is to be function, every element in the first set should be mapped to exactly one element of B. Then we can say that it is a function. Here as 3 is not mapped to any element, we can say that this is not a function. Here if you observe this is also not function because from one element in the domain we should map to only one element. But if you observe here from 3 we are having mapping to 2 elements. That's why this is also not a function. So if f is a function from A to B and f of A equal to B, then A is said to be domain of f, B is said to be codomain of f, and B is called image of A and A is called pre-image of A, and range. So what is range of f? Range of f is set of all images of elements of A. So if f is a function from A to B, then we can say that if f is a function from A to B, A is said to be domain, B is said to be codomain, and element small a in A is called pre-image and element in B is called image of A. And range contains set of all images of elements of A. So this is the basic terminology in functions. Here one example is there. F is a function from A to B. Here A is called as domain, B is called as codomain. Here element A is mapped to element B. This A is said to be pre-image of this B, and this B is called as image of A. Here one example is given. Suppose every student in a DMS class is to be assigned a grade from the set A, B, C, D, E, F. So here domain contains students in a class. Codomain will be A, B, C, D, F. Here some students are given grade. Adam is given grade A. Chow is assigned with grade C. And good friend is assigned grade B. And Rodrigue is assigned for A. And Stevens is assigned for F. So in graphically we can represent this function. Adams is assigned to grade A. Chow is assigned to grade C. Good friend is assigned to B. Rodrigue is assigned to A. Stevens is assigned to F. Here as all the elements in the domain are assigned to unique element of B, we can say that this is an example for a function. In this function we have to find domain, codomain and range. What is domain? All the elements from the first set comes under domain. So here Adams, Chow, good friend, Rodrigue, Stevens is domain. So what is codomain? All the elements in the second set A, B, C, D, F. All these are codomain. Next, what is range? Range means all the elements in the codomain which have mappings from domain. So out of A, B, C, D, F, D is not having any mapping from domain. All remaining elements are having mapping from domain. So range will be A, B, C, F only, because D doesn't have mapping from domain. That's why for this example, range will be A, B, C and F. Here one more example is given. R is a relation defined as set of all ordered pairs Abdul, 22, Brenda, 24, Carla, 21, Desire, 22, Eddie, 24 and Felicia, 22, where each pair consisting of a graduate student and the age of the student. What is the function the relation determines? Here we define the relation on between set of all graduate students and ages of the students. So here what is the domain? Domain contains all the students. Who are the students? Abdul, Brenda, Carla, Desire, Eddie, Felicia. All these comes under domain. So what is codomain? Codomain we can take set of all positive integers, because here the relation is from graduate students to age of the students. Automatically we know that age means it will be positive. So domain we will consider as all these students, and codomain we will take as set of all positive integers. Next we have to find the range. So what is a range? The values in the codomain which have mapping from domain. So for this example, 22, 24, 20, 21, 22 and 24 are having mapping from domain. So for this example, range will be 21, 22 and 24. So this is one example for one function. Next, real valued function and integer valued function. So when can we say that a function is real valued? When can we say that a function is integer valued? A function is said to be real valued if its codomain is set of all real numbers. For example, function f from A to R. For example, here f is a function from A to R. Here codomain is R. What are the value of the set of domain? If the codomain is real numbers, then it is said to be a real valued function. So f from A to R is a real valued function. Similarly, one more example, f from Z to R. What are the domain may be? If the codomain is set of all real numbers, that type of function is said to be real valued function. Similarly, integer valued function. So when can we say that a function is integer valued? So if the codomain is set of all integers, then such function is said to be integer valued. For example, f is a function from Z to Z. Here, what are the domain? What are the value of domain? If the codomain is set of all integers, then it is integer valued. As the given function is having set of integers as codomain, we can say that this given function f is an example for integer valued function. Similarly, for example, if f from R to Z, this is also integer valued, because here what are the value of domain? Here codomain is set of all integers. So this function is also an integer valued function. Hence, we can say that a function is said to be integer valued if its codomain is set of all integers. And we can observe one thing, two real valued functions or two integer valued functions with the same domain can be added as well as multiplied. That means if you take either two real valued functions or two integer valued function, if we take the same, then the addition and multiplication operations can be performed on the given functions. See one example. If let f1 and f2 are functions from A to R, then f1 plus f2 and f1 f2 are also functions from A to R. In this way, we can define addition and multiplication on functions. If f1 and f2 are two real valued functions, then f1 plus f2 of x equal f1 of x plus f2 of x, and f1 into f2 of x equal f1 of x into f2 of x. Here these are the addition and multiplication defined on two real valued functions because their codomain is R. Here one example is given. f1 and f2 are functions from R to R such that f1 of x equal to x square and f2 of x equal to x minus x square. Here we have to compute addition and multiplication. So compute addition. f1 of x plus f2 of x. What is f1 of x? X square plus what is f2 of x? X minus x square. Both get cancelled and we get x. So if we perform addition, we will get x as solution. Next find multiplication. So f1 of x into f2 of x, that equal x square into x minus x square. Multiply with it. So we get x cube minus x power 4. So for the given problem, f1 plus f2 we got as x and f1 into f2 we got as x cube minus x power 4. So in this way we can perform addition and multiplication on functions. Here one more example is given. Both f1 and f2 are two real valued functions because their codomain is R. f1 of x is defined as x plus 2, f2 of x is defined as x plus 3. We have to compute addition and multiplication. So f1 of x equal x plus 2, f2 of x equal x plus 3. Perform addition and multiplication. So f1 plus f2 of x equal f1 of x plus f2 of x, that equal x plus 2 plus x plus 3. So x plus x means 2x plus 2 plus 3 means 5. So f1 plus f2 of x we got as 2x plus 5. Next compute multiplication. f1 into f2 of x equal f1 of x into f2 of x. So what is f1 of x? X plus 2 into x plus 3. Multiply both sides. We get x square plus 3x plus 2x plus 6. That is nothing but x square plus 5x plus 6. So for the given problem, f1 plus f2 we got as 2x plus 5. And f1 into f2 of x we got as x square plus 5x plus 6. Next we will define one-to-one function. So if f is a function, then it is said to be 1-1 or an injective function if f of a equal to f of b implies a equal to b. So if f is a function from a to b, so if f is a function from a to b, we define f as 1-1 if f of a equal to f of b if f of a equal to f of b implies a equal to b. So we can say that f is 1-1 if their images are equal, then elements are also same. F of a equal to f of b, then a equal to b. That is one way of defining one-to-one function. It also can be written as if a not equal to b, then f of a also should not be equal to f of b. So we can define a one-to-one function in two ways. If f of a equal to f of b, then a must be equal to b. Or in another way, we can define one-to-one function as a not equal to b implies f of a not equal to f of b. If that condition is satisfied, then we can say that f is 1-to-1. or injective function. So we can say that f is injective function if it is 1 to 1. That is, f of a equal to f of b implies a equal to b. Here one example is given. F is defined from set A, B, C, D to 1, 2, 3, 4, 5 with f of a equal to 4, f of b equal to 5, f of c equal to 1, f of d equal to 3. We have to check whether f is 1 to 1 or not. Using diagram also we can observe. So here f is a function from A to B. What is domain? A, B, C, D. What is codomain? 1, 2, 3, 4, 5. According to the given function, A is mapped to 4, B is mapped to 5, C is mapped to 1, D is mapped to 3. So A is mapped to 4, B is mapped to 5, C is mapped to 1, D is mapped to 3. So we know that F is 1 to 1 if distinct elements of A are mapped to distinct elements of B. Here if you observe, elements are mapped to distinct elements. Hence we can understand that given function is 1 to 1. So f of a equal to f of b implies a equal to b means we should understand that distinct elements of A should be mapped to distinct elements of B. If that condition is satisfied, f is 1 to 1. So if you observe the given table, we can understand that f is 1 to 1. A is mapped to 4, B is mapped to 5, C is mapped to 1, D is mapped to 3. So distinct elements of A are mapped to distinct elements of B. Hence the given function is 1 to 1. Here some examples for functions which are 1 to 1 and which are not 1 to 1. See, if you observe this is not, given function is 1 to 1 because A is mapped to 1, E is mapped to 4, I is mapped to 5, O is mapped to 2. That means distinct elements of the domain are mapped to distinct elements of codomain. Hence this function is a 1 to 1. So if you observe this function, this is not 1 1 because here E is mapped to 2. That means f of E equal 2. O is mapped to 2. That means f of O equal 2. That means here what you got? F of E equal f of O because E and O are mapped to same element. That's why their images are equal. So f of E equal f of O. But is E equal to O? No. But E not equal to O. Hence we can say that f is not 1 to 1 because two distinct elements are mapped to same element. Hence we can say that this function is not 1 to 1. See one more example. Here domain is having 4 elements, codomain is having 5 elements. 4 elements are mapped to distinct elements of codomain. So in case of 1 to 1 codomain, there may be elements which are not mapped. Here 8 is not having any mapping from domain. Even in that case also it is 1 to 1 because if a function is to be 1 to 1, the condition to be satisfied is distinct elements of domain should map to distinct elements of B. Here R is mapped to 4, H is mapped to 2, O is mapped to 1, Q is mapped to 5. So as all distinct elements of domain are mapped to distinct elements, hence this is a 1 to 1 example. Observe this is not 1 to 1 because H and O are different, but they are mapped to same element. That means H not equal to O, but f of H equal to f of O. We know that f is 1 to 1. If H is not equal to O, then f of H must not equal to f of O. So if H is not equal to 0, according to definition, f of H must not equal to f of O. But here H not equal to O, but f of H equal to f of O. Hence, according to the definition of 1 to 1, we can say that given function is not 1 to 1. One more example. Here f is a function defined as f of x equal to x square from z to z. We have to check whether it is 1 to 1 or not. F of x equal to x square. F is a function from z to z. So we have to check whether it is 1 to 1 or not. Madam, is it confusing? F from z to z is 1 to 1 or not. Domain is codomain, both are same, z and z. For example, take 1 and minus 1. What is f of 1 square? Equal to 1. What is f of minus 1? Minus 1 whole square. That equal to 1. That means if you take 1 and minus 1 from the domain, both are mapped to same element. F of 1 equal to f of minus 1. But 1 not equal to minus 1. So given function is f is defined as f of x equal to x square and it is defined from z to z. So we have to check whether it is 1 to 1 or not. So distinct elements should have mapped to distinct elements. For example, take two elements from the domain, 1 and minus 1. What is f of 1 here? 1 square, that equal to 1. What is f of minus 1? Minus 1 whole square, that is also 1. Here f of 1 equal to f of minus 1, but 1 not equal to minus 1. Hence, we can say that it is not 1 to 1. When it will be possible means if you take domain only set of positive integer, in that case it will be 1 to 1. Instead of z to z, if you take from z plus to z, in that case it may be 1 to 1. Next we will discuss about onto function. So when can we say that a function is onto? So if f is a function a to b, then we can say that it is onto or surjective if for every element in the codomain there should be some element in the domain such that f of a equal to b. That means if f is a function from a to b, then f is said to be onto if for every element in the codomain they should be having mapping from element in the domain. If that condition is satisfied, then that function is said to be onto and it is said to be surjective. Here one example is given. F is function from a, b, c, d to 1, 2, 3 defined by f of a equal to 3, f of b equal to 2, f of c equal to 1, f of d equal to 3. Here we have to check whether it is onto or not. For example, using mapping also we can see. Here domain is a, b, c, d, codomain is 1, 2, 3. So a is mapped to 3, b is mapped to 2, c is mapped to 1, d is mapped to 3. Is f onto or not? When can we, what is the definition of onto? Every element in the domain, codomain should have mapping from domain. Here 1 is having mapping, 2 is having mapping, 3 is also mapping from domain. So by the definition of onto, we can say that f is onto. See one more example. Here this is an example for onto because here domain contains a, e, I, o, u. Codomain contains 1, 2, 3, 4. So 1 is having mapping from domain, 2 is having mapping, 3 is having mapping. So every element in the codomain is having mapping from domain. Hence the given function is onto. This function is not onto because even though 1, 2 and 5 are having mapping from domain, here 3 and 4 doesn't have mapping from domain. Hence this is not a function, onto function. So if we want to prove a function to be onto, every element in the codomain should have mapping from domain, then only it will be onto. In this example, 3 and 4 are not having mapping from domain. That's why this is not onto function. Here some more example is given. Here the domain contains 4 elements R, H, O and Q. codomain contains 4, 2 and 5. If you observe, all the elements in codomain are having mapping from domain. Hence, this is onto. Observe this, here 8 and 1 are not having mapping from domain. That's why this is not onto. Even though 4, 2 and 5 are having mapping, 8 and 1 are not having mapping. That's why this is not onto function. Some more example is given. Here these are some examples which are onto. If f is a function from set of integers to set of integers defined by f of n equal to n minus 2, it is onto. You can check on your own. Similarly, f from R to R defined by f of x equal to x cube. F from z plus to z plus by f of x equal to x square. All these are examples for the functions which are onto. Next, these are the examples which are not onto. So, if f is a function from R to R defined by f of x equal to x square, it is not onto. Similarly, f is a function from set of natural numbers to set of natural numbers defined by f of x equal to x. This is also not onto. F from z to z by f of x equal to x plus 3. All these are not onto. You can check on your own. Next, bijective function. So, when can we say that a function is bijective? So, a function is one-to-one correspondence or bijection if it is both 1-1 and onto. So, a bijective function is also called as one-to-one correspondence. So, a function is said to be bijective function or one-to-one correspondence if it satisfies both one-to-one and onto conditions. Here example is given, f is a function from a, b, c, d to 1, 2, 3, 4. So, domain contains a, b, c, d, codomain contains 1, 2, 3, 4. A is mapped to 4, b is mapped to 2, c is mapped to 1, d is mapped to 3. Clearly, this is a bijective function because every distinct elements of the domain are mapped to distinct elements of codomain. Hence, it is one-to-one. As all the elements in codomain are having mapping from domain, it is onto also. So, as the given function satisfies both one-to-one and onto, this is a bijective function. Here some example is given. This is also one-to-one because distinct elements in domain are mapped to distinct elements in codomain. That's why this is 1-to-1. As all elements in codomain are having mapping from domain, this satisfies onto also. Hence, this is a bijective function. So, if you observe this function, this is neither 1-1 not onto. Why it is not 1-1? Because A and C are mapped to same element. That's why this is not 1-1. Why it is not onto? Element 4 in the codomain doesn't have mapping from domain. That's why this is not onto. So, as both 1-1 and not onto conditions are not satisfied, we can say that this is neither 1-to-1 nor onto. Take one more example. Here this is both bijective because here domain 4 elements, here 4 elements. As distinct elements of domain are mapped to different elements of B, it is 1-to-1. As all elements in the codomain are having mapping from domain, this is onto also. Hence, this is an example for bijective function. If you observe this, this is not bijective because it is 1-1. As all elements of codomain are mapped to different elements of codomain, it is 1-1. But this is not onto because element 8 in the codomain is not having mapping. That's why this is not onto. So, this is example for 1-to-1 but not onto. Why 1-to-1? A is mapped to 3, B is mapped to 4, C is mapped to 1. as distinct elements of domain are mapped to different elements of codomain. This is 1 1, but not onto. Why not onto? Because element 2. Because element 2 in the codomain doesn't have mapping from domain. That's why this is an example for a function which is 1 to 1 but not onto. So this is an example for onto which but not 1 1. Why it is onto? Because all elements in the codomain are having mapping from domain. That's why this is onto. Why it is not 1 1? Here both A and D. A and D both are different, but their images are equal. A and D are distinct, but they are mapped to same element. That's why this is onto but not 1 1. So this is a function which satisfies both 1 to 1 and onto. Why 1 to 1? Distinct elements in the domain are mapped to different elements of B. That's why this is 1 to 1. Why it is onto? Distinct elements of codomain are having mapping from domain. That's why this is a bijective function which satisfies both 1 to 1 and onto. This is neither 1 to 1 nor onto. Why not 1 1? A and C are distinct, but they are mapped to same element. That's why this is not 1 1. How can we say that it is not onto? Because element 4 in the codomain doesn't have mapping from domain. That's why this is not onto. So this is an example for a function which is neither 1 1 nor onto. So this mapping itself is not a function, because we know that function means from one element we should map to one element. One element may have mapping from more than one element, but from one element we should not map more than one element. But in this example, from A we are having mapping to 2 and 4. From one element it is mapped to two elements, which is not permitted. So because of this reason we can say that the given mapping is not a function. Next we will discuss about composition of functions. So here G is a function from A to B, F is a function from B to C. So here G is a function from A to B and F is a function from B to C. Here composition of F and G is denoted by F circle G. So F circle G is defined as F circle G of A equal to F of Z of A. So F circle G of A is defined as F of G of A. So this is about composition of two functions F and G. This is an example. Here G is a function from A to B. F is a function from B to C. F circle G is from A to C. So this is the diagrammatic representation of composition of two functions. Note. So if A and B are two finite sets and if F is a function from A to B, then following conditions will be true. So if F is a mapping from A to B and F is 1 to 1, then cardinality of A less than or equal to cardinality of B. That means if F is a 1 to 1 function, then number of elements in the domain must be less than or equal to number of elements in the codomain. One more thing is, if F is onto, then number of elements in the codomain must be less than or equal to number of elements in the domain. And if F is a bijective function, then number of elements in the domain will match with number of elements in the codomain. Here an example is given on composition of function. G is a function from ABC to ABC. So G is function from ABC to ABC. such as g of a equal to b, g of b equal to c, and g of c equal to a. Similarly, f is a function from ABC to 1, 2, 3. So here g is a function from ABC to ABC. G a to G is a function from a to b defined as a is mapped to b, b is mapped to c, c is mapped to a. Similarly, f is a function from ABC to set 1, 2, 3, such as a is mapped to 3, b is mapped to 2, c is mapped to 1. In this way, both functions f and are defined. Then we have to find composition of f and g and composition of g circle f. So first find f circle g of a can be expanded as f of g of a. What is g of a? G of a is nothing but b. Substitute here. So f of b. What is f of b? 2. So f circle g of a equal to 2. Similarly, f circle g of b equal to f of g of b. What is g of b? B is assigned to c. So g of b nothing but c. So what is f of c? C is mapped to 1. That's why f of c equal to 1. Similarly, find from f circle g of c. So f of g of c. What is g of c? C is assigned to a. So g of c is nothing but a. So f of a. What is f of a? A is mapped to 3 here. So f of a equal to 3. In this way, we find composition for f circle g. So when we are finding f circle g means we should take in reverse a. So f circle g means how we will compute? We should come from g. G is from ABC to 1, 2, 3. ABC to ABC. F is a function from ABC to 1, 2, 3. Here composition is possible because codomain of G is mapping with domain of F. That's why here composition is possible. But in case of G circle F, in codomain of F doesn't map with domain of G. Hence, composition of G circle F is not possible here. So when we want to find the composition between two functions, one codomain of one function should map with domain of another function. Then only composition will be possible. Here one problem is given, f of x equal 2x plus 3 and g of x equal 3x plus 2. We have to find f circle g and g circle f. So here f circle g of x is nothing but f of g of x, that equal to f of, what is g of x? 3x plus 2. So in place of f of x, substitute 3x plus 2. So 2 into 3x plus 2 plus 3. So 6x plus 4 plus 3. So 7. So for this problem, f circle g of x equal 7. Similarly, find g circle f of x. So g circle f of x equal g of f of x. So what is f of x here? F of x is 2x plus 3. So we got z of 2x plus 3. What is z of x? 3x plus 2. So here in place of x, substitute 2x plus 3 here. So we get 3 into 2x plus 3 plus 2. If we expand this, we get 6x plus 9 plus 2. So 6x plus 11. So for the given problem, f circle g of x will be 6x plus 7 and g circle f of x equal 6x plus 11. In this way, we can find f circle g and g circle f for the given function. Next, inverse of a function. So given f, a one-to-one correspondence function from a to b. That means if we want to prove that a function has inverse, first it must be a bijective function. So if a function is 1, 1 and onto, then only we can find inverse for that function. So if we define a function f from a to b, then its inverse function is defined from f inverse from b to a. So if f is a function from a to b, f of a equal to b, it can be written as f inverse of b equal to a. In this way, we can find inverse of the given function. So this is a diagrammatic representation for finding inverse of the given function. Here some examples. Here f is a function from x and y defined as 1 to 4, 3 to 6, 4 to 0. Then its inverse will be domain and it will be interchanged. So 4, 6, 0 will be domain, 1, 3, 4 will be codomain. So in case of inverse function, domain and codomain will be interchanged. So here 1 to 4 mapping, it will change to 4 to 1. Here 3, 6 mapping, it will change to 6, 3 mapping. Here mapping from 4, 0, it will be converted to 0, 4. In this way, we can find inverse of a function. Here one problem is given, you have to find the inverse. Y equal 2x minus 4. So here problem is y equal 2x minus 4. So for this problem, you have to find the inverse function. So first, this is nothing but f of x. So first, what is the step? Switch x and y. So as the first step to find the inverse, interchange the values of x and y. Then it becomes x equal to y minus 4. Then add 4 to both sides. Then we will get x plus 4 equal to y. Then divide 2 with 2 on both sides. We will get 1 by 2 into x plus 2 equal to y. So this is the inverse for the given function. So for the given function y equal to x minus 4, inverse function will be 1 by 2 into x plus 2 is the inverse. One more example is given. Here y is defined as x by 5x minus 3. This is given. For this problem, you have to find the inverse. What is the first step? Interchange the values of x and y. So this become x equal to y by 5y minus 3. Then cross multiply it. Then we will get 5 into xy minus 3x equal to y. Then what you get? Take y to left side and 3x to right side. Then it will become 5xy minus y equal to 3x. So from these both terms we can take y as common. So if you take y as common, we get 5x minus 1 into y equal to 3x. Take this 5x minus 1 to right side. So we will get y equal to 3x by 5x minus 1, which will be the inverse for the given function. So for the given function y equal to x by 5x minus 3, 3x by 5x minus 1 is the inverse. In this way, we can find inverse for the given function. Next, for finding inverse of the power functions. For example, here f of x is given like this. 1 by 1 f of x equal to 1 by 16 into x power 5. This is the given. For this function, you have to find the inverse. Same process. Interchange x and y. So this will be x, f of x is nothing but y. So this is nothing but x equal to 1 by 16 into y power 5. Cross multiply on both sides. We will get 16 into x equal to y power 5. What you have to find? Y. Here fifth root is there. So multiply this. Both sides, take fifth root. Then we will get 16x whole power 1 by 5 equal to, we will get y. So y equal 16x whole power 1 by 5. That is the inverse for the given power function. So this is the process for finding inverse for the power functions. Next, cubic functions. So how to find inverse for the cubic functions? Here example, f of x equal to x cube plus 4. We know that f of x is nothing but y. So y equal to x cube plus 4. Interchange the values of x and y. We get x equal y cube plus 4. Take y to left side. Then we get x minus 4 equal y cube. Here right side cube is there. So multiply with x power 1 by 3. 1 by 3. X minus 4 whole power cube root means 1 by 3 equal to y. What is y? F of x equal to y. Then y is nothing but f inverse of x. Therefore, f inverse of x equal cube root of x minus 4. So, cube root of x minus 4 is the solution for the given cubic function. So, in this way, we can find inverse for the cubic functions. Next, identity function. So, if you take any composition between one function and its inverse function, suppose f is a function, then its inverse function will be f inverse. So, if you take composition between one function and its inverse function, then we will get identity function. So, it is denoted by I of x equal x. So, composition between a function and its inverse function is nothing but identity function and is defined as I of x. So, I of x will be always equal to x. This is about identity function. Next, graph of a function. So, if we can represent any function using graph also. For example, if you take f of x equal to x square. In graph form, we can represent like this. So, this is the graphical representation of the function f of x equal to x square. Next, we will discuss about floor function. So, what is the floor function? It is denoted by this symbol. So, this is the symbolic representation of the floor function. So, what does a floor function do? Floor function assigns to the real number x the largest number that is less than or equal to x. For example, if you take any value between 1 and 2, it will be 1. If you see the example, you can observe. Floor function will assign the largest integer that is less than or equal to given number. Here we are finding the floor of 2.3. So 2.3 will be assigned to 2 because what are the integers less than that number, less than 2.3? 0, 1, 2 are the integers. So among the integers which is less than 2.3, we have to find the highest one. So among 0, 1, 2, 2 is the highest. That's why floor function of 2.3 is assigned with 2. So floor function of a function will assign the largest among its numbers less than that number. Here 2, it will be as it is 0.5. So the integer which is less than 0.5 is 0. As itself is the largest, floor function of 0.5 will be 0. Minus 3.5 floor, minus 4. In that way, floor function will assign the largest integer among the numbers which is less than or equal to that number. So if in case of 2.3, 0, 1 and 2 are the integers which are less than these numbers. Among these, 2 is the largest. That's why floor of 2.3 will be 2. Next we will discuss about ceiling function. So if x is a real number, ceiling of x is represented by this symbol. So ceiling function will assign to real number x the smallest integer that is greater than or equal to x. Symbolically, it is denoted by this symbol. So, ceiling function of x will assign the smallest integer that is greater than or equal to x. For example, here ceil of 2.3. So, what are the integers greater than 2.3? 3, 4, 5 and so on. So, among all the integers, 3 is the least. Hence, ceil of 2.3 will be 3. Next 2 as it is 0.5. So what are the integers greater than 0.5? 1, 2, 3 and so on, etc. Among these, 1 is the least. That's why CL of 0.5 will be 1. Similarly, CL of minus 3.5 is minus 3. In this way, we can find ceiling function values. So these are some properties of floor function and ceil function. So floor of x will be n if x is in between n and n plus 1. This is ceil. Ceil of x will be n if x is in between n minus 1 and n. And floor of x will be n if x minus 1 less than x less than or equal to x. Similarly, ceil of x will be n if n is in between x and x plus 1. So all these are various important properties of floor function and ceil functions. Here some problems are given. Here are like f of x equal to 1 by x, f of x equal to root x. We have to define the reason why f is not a function from R to R for f of x equal to 1 by x. If you take 0, 1 by 0 means it is not defined. As f of 0 is not defined, that's why we can say that first one is not a function. So why this one not a function? Root x means sometimes we may get a negative value. For negative values, it is not possible. That's why it is also not function. So for negative value of x, this function is not defined. That's why both given are not functions. Here some problem is given. You have to find the domain and range. Here the function that assigns to each bit string the number of ones in the string minus the number of zeros in the string. So here what is the domain? Bit string will be the domain. So bit string to bit string what it will assign? Number of ones in the string minus number of zeros in the string. That means integer, some integer. So domain will be set of all bit strings, range will be set of all integers. See second bit, for this bit also you have to find the domain and range. So what is the domain? Bit string. Set of all bit strings is the domain. What is the problem? The function that assigns to each bit string twice the number of zeros in the string. That means what it will assign to bit string? If there are two number of zeros, it will be assigned 4. That's why domain for this problem is bit strings, range will be set of all even non-negative integers. Here the function that assigns to each pair of positive integers the maximum of 2 integers. So what is the problem? We have to find the domain and range. So what is the domain here? Pair of positive integers. Pair of positive integers. That's why domain will be z plus cross z plus. What is the range? Z plus. Here we have to find the ceiling function and floor function values. So this is ceil of 3.4, 3 by 4. 3 by 4 means 0 point something. So nearest to integer value will be 1. What is the second one? Floor of 7 by 8, 0 point something. So we will get 0. See the third one, C bit, 0, D bit, minus 1, E, same, 3, F bit, minus 1, Z, 2, H, 1. In this way, we can find floor function and ceil functions for the given problem. So here problem is, if f and f circle g are onto functions, does it follow that g is also onto? Here what is given? F is onto. Similarly, f circle g is also onto. We have to check whether g is also onto or not. We have to justify with answer. Here answer is no. That means even if f and f circle g are onto, g need not be onto. Here example is given. A is defined as element containing A, B contains BC and C contains D. Here G is a function from A to B. What is G? A is assigned to B. F is a function from B to C. Here it is B is assigned to D, C is assigned to D. So here F is onto because every element in the codomain is having mapping. So here F is onto. Similarly, F circle G is onto. But here G is not onto because here B is having mapping from A. But C doesn't have mapping from domain. That's why G is not onto. So from this example, we can conclude that even though F and F circle G are onto, G need not be onto. With this example, we can prove that. Here f of x equal to x square plus 1, g of x equal to x plus 2. We have to find f circle G and addition and subtraction. Here f is the function from R to R defined as f of x equal to ax plus b is invertible where a and b are constants. Here f is defined as R to R defined as f of x equal to x plus b. We have to find its inverse. When can we say that f is invertible? If it is 1 1 and onto. F is 1 1 because if you take f of x1 equal to f of x2, we can get x1 equal to x2 because here take f of x1 equal to f of x2. What is f of x1? Ax1 plus b equal ax2 plus b. Get a and b gets cancelled on both sides. We get x1 equal to x2. So f of x1 equal to f of x2. From this we are able to get x1 equal to x2. Hence f is onto 1 1. Similarly f is onto because in place of x, if we substitute y minus b by a, we will get the mapping. So as f is 1 1 and onto, we can say that it is invertible and y minus b by a is the inverse for the given function.